Hey everyone, we'll go ahead and get started. Welcome to the last seminar of this academic year. Thank you everybody for attending and participating so thoroughly all semester. We really appreciate it. Of course, there will continue to be a handful of completion seminars over the summer, so I encourage you to attend those when you can. I know everyone will be busy with field work and spread out all over the state or country or continent, but those students need support in their completions as well. So today I'd like to introduce our last speaker for the semester, Lyntausha Kuehl is going to tell us about a statewide assessment of drivers influencing biotic integrity in perennial wadeable streams of South Dakota.
Thank you for the introduction. Thank you everyone also for showing up today, and thanks also to the people joining us remotely. So Great Plains streams are harsh environments by nature. Within the Great Plains region, we have a precipitation gradient from east to west and a temperature gradient from north to south. Both of these climate characteristics also exhibit strong seasonality. Within streams and rivers themselves, we also have high spatial and temporal variability. For example, the magnitude, duration, and frequency of flood and drought events can vary from year to year and location to location. We can also see differences in other features like water clarity over relatively small distances and time spans. For an example, the two pictures shown off to the right are taken from the same spot in the South Fork of the Bad River, only 1 month apart. And so you can see quite a big difference in terms of water flow, water clarity, and vegetation. There's also harshness because of anthropogenic impacts and land use patterns. In the state of South Dakota, cultivated agriculture dominates east of the Missouri River, and rangeland grazing dominates to the west. Both of these have known impacts on stream quality. For example, cultivation can increase sedimentation and nutrient enrichment, can modify channel morphology, and can alter hydrologic cycles. Cattle grazing, especially at high intensities, can also increase sedimentation, can alter banks, and can also modify riparian vegetation and condition. In the state of South Dakota, approximately 47% of the land area is devoted to pasture land, 38% to cropland. And considering that agriculture is the #1 industry accounting for about 20% of the economic activity in the state, these numbers are not likely to go down. Together, these conditions result in a challenge for water resource managers. These managers need to be able to differentiate and account for variability in natural and anthropogenic induced systems. They also need to be able to detect impairment and to identify the cause for that impairment. One method for detecting impairment is the Index of Biotic Integrity, or IBI. It's a multi-metric index that was first proposed by James Carr in 1981 to integrate information from multiple scales into a single ecologically based index. South Dakota has a long and proud history of IBI development east of the Missouri River, spanning several projects going all the way back to the late 1990s. The latest project was focused on the Northern Glaciated Plains, or NGP, ecoregion of South Dakota, and was designed to develop both fish and macroinvertebrate IBIs for that ecoregion. This has in turn led to the project I've been working on, which is doing the same thing in developing fish and macroinvertebrate IBIs for the Northwestern Great Plains, or NWGP, ecoregion in western South Dakota. Now I will make a note here, I am only dealing with the macroinvertebrate assemblages from the NWGP project. Also, I was not personally involved in the collection or analysis of data from the NGP project, but I was allowed to use it within combination of my own data to do statewide analyses. The objectives of my project were to develop the macroinvertebrate IBI for NWGP perennial wadeable streams. We also wanted to evaluate for level 4 ecoregion differences in IBI scores, specifically within each level 3 ecoregion, so in the NWGP or in the NGP. And we felt that there would be at least one given the variability in topography and land use across the state. Third, we wanted to identify proximal drivers of biotic integrity. So what characteristics within the stream are relating to or driving changes in biotic integrity? And we felt that important drivers would relate to cultivation, grazing, and soil erosion. And finally, we wanted to evaluate if regional variables were acting as important drivers of in-stream habitat. We felt that they were, but we wanted to actually test this. So this is a map of all the study sites used in my statewide analyses. Level 3 ecoregions are outlined in black. Level 4 ecoregions are indicated by different colors. To the right, in more of the red shades, we see the NGP project sites. Those are selected using targeted classification of sites and sampled in 2010 and 2011. To the left, in the blue colors, are the NWGP sites where my work is focused. We use stratified random sampling to select sites across 8 level 4 ecoregions and then sampled them in 2014 and 2015. Total, we have 96 sites involved in our analyses across the state. Methodologies for the 2 projects were identical. So in the field, we used regional environmental monitoring and assessment program protocols from the EPA to collect our data. When we got to a site, we used a function of stream width to delineate a sampling length, or each length, and that was divided evenly into 11 equally spaced transects, such as those shown here. Those transects were then used as markers for us to decide where we were going to be collecting our data. Chemistry data was collected first to avoid contamination by us moving around in the stream. Biological data was collected second. For macroinvertebrates, this meant taking a D-frame net sample at each transect in a zigzagging pattern through the entire length of the reach, and then combining that into a single sample for each site. And then finally, at each transect across the reach, we collected a multitude of physical habitat data. Now, we took a lot of measurements, but basically they broke down into characterization of bed substrates, channel characteristics like morphology and vegetation, and water chemistry information, including turbidity, nitrate concentrations, sodium concentrations, and dissolved oxygen. These constitute the in-stream habitat variables that we used in our analyses. Also, as a component of each project, GIS tools were used to derive watershed characteristics using digital data layers, including characteristics in the riparian zone, such as cultivation within 30 meters of the stream, and total watershed characteristics like percent barren ground, percent herbaceous cover, and an integrated watershed conditions score. These represent the watershed variables in our analyses. To process our invertebrate samples, we used wadeable stream assessment benthic laboratory protocols from the US EPA, which we used to pull a minimum of 300 individuals out of each sample, and then we identified each of those individuals down to the lowest level required or possible, typically to the genus level. To develop our IBI, we first had to calculate a suite of metrics describing the biological assemblages. These fall out into 5 classes: abundance and composition, richness and diversity, functional feeding guilds, habit guilds, and tolerance. In the NGP project, they calculated a total of 90 metrics across these 5 classes. In the NWGP, we calculated the same 90 metrics and included 13 new ones. These lists of metrics then had to be cut down to only those that would best detect impairment. And this was done using the Whittier et al. Method from 2007, which is a series of 6 statistical tests that eliminate unresponsive or uninformative metrics. So first, we use a range test to eliminate metrics that have small ranges and can't distinguish between sites very well. We also use a signal to noise test to look at the variability in our metric values over space and time, and highly variable metrics were also eliminated. Third, we measured the metrics correlation with watershed area, which was our natural gradient. And then we could correct those metric values for that, so we didn't actually eliminate metrics with that step. Fourth step was a response test. We wanted to get rid of metrics that were going to not be able to distinguish significantly between impaired and non-impaired sites. A redundancy test was used to eliminate metrics that will give us the same information as a better performing metric also on the list. And then finally, we look at another range test for metric values. We don't want to keep metrics that overlap in scores between the impaired and non-impaired sites, because then they're going to score sites very similarly. After that, we have the final metrics to be included in our IBI. From there, we still have to create the IBI scores. And to do that, we give each metric value a score ranging from 0 to 10. The zeros are given to metric values at the 5th percentile or below, 10s are given to the 95th percentile and above. However, if that metric value is expected to decrease with increasing biotic integrity, we reverse that, the 5th and 95th. Then we linearly interpolate to get the rest of the values between 0 and 10. At that point, we have individual metric scores, which we can then sum up to get an IBI sum. That then is rescaled, so it gives us a final IBI score ranging from 0 to 100. To compare our IBIs by ecoregion, we used a qualitative evaluation of looking at the list of metrics included in each IBI and comparing how much they overlapped. And then we used KW NOVAs to try and detect significant differences by level 4 ecoregions. To analyze our abiotic drivers, we used a combination of techniques. So first, we combined the macroinvertebrate assemblages from the NGP project and our own NWGP project into one data set, and then ran cluster analysis to identify biologically similar groups. Those groups were then compared to level 3 ecoregion, level 4 ecoregion, and river basin to see if those natural regions would match up with the groupings or not. We also use non-metric multidimensional scaling to ordinate and plot those groupings and overlay correlation vectors to try and identify drivers of our assemblages as a whole. The bulk of the analysis, however, was iterative random forest modeling. So random forest modeling is a type of classification and regression tree or CART analysis, which is a recursive partitioning technique that uses predictor variables to split the data into increasingly homogeneous groups, resulting in a tree like this one. Random forest modeling creates a multitude of these trees. In our case, we created 1,000 trees within each model, and then averages results across those trees to improve model performance. That also allows us to calculate the relative importance of each predictor variable to the overall model. So what we did for this step was, for each response variable, we first ran a full model with all possible predictor variables. Then we calculated the relative importance of each and eliminated the least important variable, and then ran the model again. And then we repeated this step over and over until we only had one variable left in the model. Each step of the way, we kept track of the mean square error and the percent of variance explained by each of those iterations. The final model was the one that had the lowest mean square error and the highest percent of variance explained. We ran 3 sets of these models. The first set, we used our overall IBI score and our biological component biological metrics as our response variables, and in-stream habitat characteristics as our predictor variables. In the second and third set, in both of those sets, we're trying to identify important drivers of in-stream habitat, so those were our response variables. In one set, we used just watershed metrics as our predictors, and in the other set, we used the combination of watershed metrics and regional variables, level 3 ecoregion, level 4 ecoregion, and river basin, to try and get an idea of how important the regional variables might be as drivers. Now, before I get into the results of our stuff, providing a little context. Beneficial use attainment is an important aspect of assessment in the state. Currently, there are 11 beneficial uses assigned to waters in South Dakota. So I have those listed here. In the second column, I have the number of times the numeric criteria for each beneficial use was violated using our NWGP data. And then in the third column, we have the total river and stream miles not supporting that beneficial use according to the 2016 integrated report. So what we're seeing is that of the 11 beneficial uses, 7 of them are showing multiple violations of numeric criteria in our limited data set for the NGP, or NWGP. What's driving that non-support? Well, these are 7 important stressors identified by the SDDENR in their integrated report as stressors for non-support. And we can see again that 6 of these are showing violations within the NWGP data. And that includes things like total dissolved solids, total suspended solids, salinity, and dissolved oxygen. So these are important drivers of beneficial use attainment and important to state water resource managers. Getting into our results. After optimization, the NWGP IBI was found to have 4 metrics, which corresponds to the same number of metrics that were found in the NGP IBI. In the NGP IBI, they had Hilsenoff Biotic Index, HBI, which is a measure of the average pollution tolerance of the assemblage, the caddis-fly generic richness, percent abundance of climbing taxa, and percent abundance of insects. In the NWGP IBI, we also had the Hilsenoff Biotic Index, but beyond that, we had family richness, generic richness of non-insects, and generic richness of mayflies, stoneflies, and caddisflies. Given that the same methodology was used to collect, process, and analyze these macroinvertebrate assemblages, the fact that we end up with very different metrics in our IBIs indicate that there's some biological differences between the 2 level 3 ecoregions. In terms of scores, because they are biologically different, we cannot directly compare an NGP score to an NWGP score, but we can look at level 4 ecoregion differences. So in this plot here, each of these boxes indicates the range of values, of score values, for each level 4 ecoregion. So the box runs from the minimum value to the maximum value. The middle line, black line, indicates the median value, which is also listed in the box. To the right of the vertical black line, we have our NGP level 4 ecoregions. Overall, scores in the NGP range from about 24 to 100, with a median value of about 52. And we can see that by level 4 ecoregions, there seems to be less variation and fair amount of overlap in the score ranges. To the left of the black line, we have our NWGP level 4 ecoregions. Overall scores there range from about 21 to 90.5, with a median value of about 42. And here we see less overlap in our ranges. So when we do our KW ANOVAs, we don't find any significant differences between level 4 ecoregions and the NGP, but we do find that the one boxed in red is significantly different from the two in green in the NWGP. So we're seeing level 4 ecoregion differences in our IBI scores. Cluster analysis identified 8 biologically similar groups. 3 of these were dominated by sites from the NGP, indicated by red, and the other 5 were dominated by the NWGP. But we didn't have as good of a breakdown by level 4 ecoregion or river basin. So this biological separation between the two is upheld in our NMDS plot, where we see that the 3 groups dominated by NGP sites in red tend to cluster towards the top of the plot, and our NWGP dominated groups tend to cluster towards the bottom, shown in blue. This seems to follow along a land use gradient along axis 2, which explains 61% of our variance. So we have nitrogen loading, pasture and hay, and human use more positively correlated with our NGP sites, whereas we have herbaceous cover and turbidity corresponding more with our NWGP sites. Results from our random forest modeling show that we can explain between 17 and 56% of the variance in our biological metrics and our overall IBI score using 24 in-stream physical and chemical characteristics. Of these 24 characteristics, the ones shown in red on this table are those, as you may remember, that showed significant stressors for non-beneficial use support in the state in the integrated report. So our IBI results and our IBI in general is accounting for and drawing on variation within these water quality criteria as well. Overall, IBI scores were related to salinity, measured as sodium absorption ratio, discharge, riffle length, gravel, larger substrates like cobble and boulder, and dissolved oxygen. These 6 components also show up in the models for each of the individual biological metrics. However, it's also important to note, as you can see, we have a different number and set of components for each of the individual metrics, which indicates for us that each component of the IBI is affected slightly differently by the environment, which is important for managers to know when they're trying to assess impairment or effects on biotic integrity. When we're delineating our drivers for our in-stream habitat, when we just include our watershed metrics as predictor variables, we can explain between -10 and 39% of the variance in our habitat characteristics. The negative values just mean that we had more variance in the model than in the data itself. The average was about 14%, and our poorer performing models tend to be those for substrates, total suspended solids, temperature, and width-to-depth ratio. However, the most frequent model components that showed up in our final models were measures of herbaceous cover, both within the riparian zone and within the watershed, nitrogen loading, and human use. And if you recall, that corresponds pretty well with the land use gradient that we saw in the NMDS. When we include our region variables, which are level 3 ecoregion, level 4 ecoregion, and river basin, we can explain between -5 and 76% of the variation in our in-stream habitat, averaging 24. So on average, we're increasing the variance explained by 10% just by adding these 3 variables. They often also replaced other variables in the models. A couple of extreme examples here. For our salinity measure, the original model contained 5 variables that explained 28% of the variance, and in the final model, we ended up with only 1 variable, level 4 ecoregion, that explained 76% of the variance in our salinity. And a similar story for clay. The most frequent components of these models were level 4 ecoregion, river basin, herbaceous cover, and nitrogen loading. So what do we pull from all of this? Well, we have distal drivers, our riparian features, our watershed features, and our regions that seem to be, at least in part, affecting or laying the foundation for our proximal drivers, our bed substrates, our channel characteristics, our water chemistries. Those are directly affecting our biological assemblages and subsequently the biological metrics we're calculating, which in turn are integrated into our overall biotic integrity description in our IBI. So our IBI is able to account for or draw on information from all these scales and really integrate it. So we found that IBIs differ by ecoregion. We have different metrics by level 3 ecoregion, and we're seeing some differences in scores by level 4s. We identified major drivers of biotic integrity and of in-stream habitat, which include things like salinity, dissolved oxygen, herbaceous cover, and human use in the watershed. And finally, we did find that regional variables seem to be important drivers of in-stream habitat, given that they seem to increase our the percent of variance explained in our models, and they also showed up most frequently when they were included in models. For management, this means that we recommend that a stratified or regional approach to monitoring assessment is taken. We're seeing biological differences by level 3 and some by level 4 ecoregions. We're also seeing not only abiotic differences by each ecoregion, but also ecoregions acting as drivers of that. In terms of direct applications of this, South Dakota DENR currently uses the NGP-IBI in their assessment efforts. Shown to the right is being involved in the assessment of narrative nutrient criteria, and they're constantly adding new data and new sites to keep calibrating that. And the NWGP-IBI that we just generated will be adopted and utilized in much the same way. Also, we identified our biotic-abiotic relationships across the state, which are good preliminary information for managers as they make assessments, but we've also been able to tie our IBI scores to existing water quality criteria. So essentially linking the bioassessment tools we're providing the state with their existing chemistry and physical and chemical assessment tools that they use. Future research, there's a few things that it needs to focus on. First of all, continuing to collect data to calibrate and validate these results. Secondly, to continue evaluating additional potential drivers. There's a lot that we measured and included, but there's a lot that we also didn't or couldn't measure. So for instance, direct measurements of geology across all the sites could improve substrate models, for instance. Also, there's a few blank areas on the map, such as the Black Hills and the northwestern glaciated plains, where no IBI work has been done. So IBIs could be developed for those regions, or for other water bodies, such as lakes or non-perennial streams. And with that, I'd like to briefly take some time to thank everybody on this slide for funding and space and equipment, help in the lab, help out in the field, and even permissions to go out and sample. I couldn't have done it without everybody on there. And also thanks to my committee members for being here today, as well as all their advice and help during my career. And with that, I will take any questions. Yes.
So your analyses obviously were focused on the macroinvertebrates. Do you think your results would have changed any if you had another group of species that you did? So we've done like a lot of fish IBI work, right? And some of that's in progress. Do you think the fish IBI results would be different?
Yes, from everything that I've read, I can't say for sure that they would be different within the state. Obviously, each region in each state would be different. However, from what I've seen of several papers that were looking at the correspondence of macroinvertebrate measures of integrity or macroinvertebrate assemblages and their major drivers to fish or periphyton, they overlapped in some respects, but a lot of times they tended to relate to different drivers, or they tended to not correspond with each other quite as well. So I wouldn't expect to get the exact same results for our fish assemblages in the state. Yes?
So why didn't you, since you're looking at perennial streams, stratify by discharge?
Well, out West River, I think I don't have a pretty good answer exactly in terms of why we didn't stratify. I know we had a wide range of discharge values in our streams across the region. We had some that weren't discharging very much. Most of ours were tributaries, so they weren't perennial and they were wadeable, but we only had a few sites that were on actual rivers that would have larger discharges that would only represent, let's see, 3, 4, 5, less than a tenth, about a little over a tenth of our sites would be significantly higher. So in terms of answering exactly why we didn't directly measure or stratify by discharge, I don't have an exact reason. I just know we covered a wide range of variables. We did try to use natural gradients, correlation with that for watershed area as kind of seeing if they were correlating highly with our watershed area, which we think would feed into discharge differences, and they didn't seem to at that point. other than, sorry, I can't fully answer your question. And my quick apologies. For those remote viewers, the first question I was asked dealt with whether or not I thought that these results would be the same for the fish assemblages and the fish IBIs that were generated for the same projects. And the second question asked why we didn't stratify our stream sites by discharge. Any other question?
Yeah, as a follow-up to Jeff's question, did you control in any way in the design for discharge? I mean, you mentioned it a little bit, but not really. The basic design feature of the project was to focus on wadeable streams.
Right, so they couldn't have too much of a discharge to them because they wouldn't be wadeable. We also couldn't sample a site if it was beyond bankful. So there were a couple of sites, for instance, that South Fork of the Bad River picture. The first one was actually a day it was above bankful and we couldn't actually sample, and so we sampled it only when it was below bankful and was actually wadeable and able to get in there. Yes.
I know the IBIs are scalable within the ecoregions, right? But looking at the graph, it looked like the East River streams were in generally much better condition than West River. That seems opposite of what the reality is. Is that
Yeah,
just
we were, the question from the audience this time was the fact that the IBIs are scalable within each ecoregion, but the East River IBI appeared to show higher distributions overall than the West River IBIs, which is surprising. And that caught us by surprise as well. We expected that the higher direct human impact through cultivation and urban development in the NGP would result in a differences in the IBI scores, that they would be lower. The relative differences, I mean, the NGP scores seem to be skewed, or seem to be a little bit higher in their centrality of the distribution than the MWGP. The relative difference isn't super big, about 10, which could have an impact, but isn't super big. It's possible that the natural conditions west of the Missouri River would seem degraded relative to East River in terms of easily erodible soils, resulting in less clear waters, tends to have finer substrates. They tend to dry out more, there's less precipitation, it's more erratic out there, have more alkaline and saline soils out there. So it could be making it look like those are degraded, but we essentially are covering the same range of conditions, from that 0 to about 100 in terms of score overall. So we are picking out metrics that are successfully and properly describing a range of conditions important for that ecoregion. So
is it fair to say the normal conditions, West River, minus anthropogenic stuff, is harsh to begin with, that since catching up some of the noise? Could also be fair to say that East River have such a history of degradation that happened before the study, that our normal good sites may not be as good as they could have been previously. So it's somewhat skewed on how the land use history.
that's a fair assumption. I haven't been able to tease out exactly why those are it, but I'm looking into things like that to try and figure out why we're seeing this unexpected difference in central distributions of our scores. Good question, yeah?
Lyntausha, are your major species the stonefly and I forget what the other two you mentioned?
The mayflies, stoneflies, and caddisflies?
Do they like larger or coarser substrates, or is it something that has more finer substrate?
It depends by the species. For example, mayflies can have swimming ones that don't rely quite as much on substrate. They go from vegetation and swim to other pieces of vegetation. There are clingers that actually cling to coarse substrate. A lot of the caddisflies are like that as well, so they would prefer having coarser substrates. And there's even burrowing mayflies that would prefer to have finer substrates to burrow into. So it depends a little bit on species, but overall, they do tend to favor larger substrates overall, and cleaner ones. Stoneflies, for example, we only found those in the White River, so there weren't a lot of coarse substrates that we found in our sampling site, but we did find that was the only spot we found stoneflies.
Because I was just thinking the geology is vastly different, with the glaciated versus non-glaciated.
Right.
And it seems to me that I would expect to have lower scores based on the conversation we're having with Brian, that, you would have finer particles, plus the precip is not as great, so I would think you'd have lower scores.
Right, that certainly played into it. We did have some sites For example, Whitewood Creek out near Spearfish, that had a lot of coarse substrates within it. And there were several of our sites located around the NWGP that did have some of those coarser substrates, which I think is why such as the EPT richness came out as a metric for detecting impairment, because we did have that range in our substrate
And
scores.
that one comes out of the Black Hills, right?
Right, that is fed out of
So
the
that
Black
makes
Hills.
sense.
Yeah. But yes, that is another component that could be explaining. There's a lot of complex, I almost put a plot up in here showing all the interactions of everything affecting the in-stream habitat, which is all affecting the components, which is affecting the IBI, and it just gets too complicated, so I couldn't show it in here. So the relationships are very in-depth, and there's probably a lot going on that's resulting in differences between ecoregions. And I don't think I repeated that question. So for the remote people, he was asking about the preferences of our mayflies, stoneflies, and caddisflies for substrates, and whether or not that could explain some of the differences in NGP versus NWGP IBI scores.
So does anyone remote have any questions? Any other questions from the audience?
Yes?
This might be a random question. How important was that SAR value, the SAR value? Or was that just a side note that you mentioned?
How
Sodium
important was the SAR?
absorption ratio?
How important was it, or how to be calculated?
Was that a major factor or was that a side note to your research? I'm just curious.
It was actually, in terms of the IBI on that table that I showed, the components for each model, for each biological component, those were from most important in terms of the relative importance to the model to least important. So SAR came out as the most important model component for overall IBI, and then it was towards the top for several of the other ones. So that became an important one. It also showed up in the NMDS, but it only had an R-squared of 0.1, so it didn't make my final plot. But
Right, and just so you know, have you looked into what Cheryl Reese and Doug Mail have done with that value?
no, I have not at this time.
It might be something worth looking into because I think the original metric was from California and they've recently updated it for South Dakota. So it might be worth looking at that calculation.
Okay, thank you very much. The question was about the salinity measurement, the SAR ratio that we were calculating, and its relative importance in our models, and follow up on that. Yes?
Hey, Lyntausha, I got curious about how you measure your each side repeatedly within the year or between the year, and does seasonality or affect your IBI scores?
Yep. So each site was sampled once in 1 year and once in the following year. So we had 2 growing seasons of sampling. In the NWGP alone, we had 65 unique sites, 121 sampling visits. So we visited 60 sites each year. And in terms of the IBI scores, the signal-to-noise ratio accounts for variation between years because it's a ratio of the variance between metric values of different site locations relative to variance in metric values between site visits. And if your variability between site visits is too high, it drives the ratio down, and then those metrics are eliminated. We have a cutoff point for that variability in there. So the NGP sampling was done much the same way. They had sampling in 2010, they visited all the sites, and then they visited them all again in 2011. And then, so the highly variable metrics would have been kicked out by our signal-to-noise test, and then they wouldn't have affected our IBI scores. But I'm sure there are things that happen between 1 year and the next. For example, if you sample once in a drought year, once in a flood year, that you can't control for, and that could affect some of the metrics and some of the IBI. And the question was related to how often we sampled sites and how that might affect the IBI scores. Any other questions?
All right, thank you, everybody.